morning, pre-calc, and welcome back for another lesson. Today we're going to talk about something called a logarithm, okay, or log. So some of you maybe have heard of this, although I'm guessing lots of you have not been exposed to it that much. Although in Algebra 2 we started to talk about these concepts, but it kind of happened last year right about when schools started shutting down, and so depending on who you had, you may have not talked about it as much detail as others. So kind of the purpose of our logarithm is it's going to help us to solve exponentials. It helps us solve, for example, if I have 2 to the x equals something, it helps me figure out what that x value is. Okay? And a logarithmic function, right here, the way we would read this, it's log base b of y equals x. And that's true if and only if b to the x equals y. Okay, now these two forms, they are related to each other. They're just two different ways to write it. The one on the left is known as our log form, and the one on the right, which we already worked with last week, is known as our exponential form. All right, now both of these have something called a base. If you look here, the base of the log is the little number below it. The base of our exponential we know is the normal size number that is raised to some power. So the b for both of those is the base. So if we're trying to switch between these two, the easiest way I have for you to remember it is this little saying, base stays base, and then the other two switcheroo. And I'll show you what that means in just a second. And yes, switcheroo is kind of just a made-up word. So I put two O's on it, but yeah. Base stays base, the other two switcheroo. And I did not write switcheroo very well. Let me rewrite it. It's hard enough to figure out a made-up word, but when it's crammed like that, it's even harder. So the other two switcheroo. Now, what I mean by that, if we look here, remember the base is the b. So if we were rewriting this, right now it's in log, we want to go to exponential. Okay, so when it's log to exponential, that means our final answer is going to have no more log in it, because we are now in exponential. Okay, so base stays base means 2 will still be the base. Other two switcheroo, meaning 2 was beside the 32. Now, if those two switch places, the 2 will be on the same side as the 5. So it's 2 raised to the 5th equals 32, which hopefully you guys know if we take 2 to the 5th, we will get 32 as our answer. Okay, so the next one, base stays base. So right here, this 7 stays as the base. The other two switcheroo, meaning it was beside the 7, so now it's going to be beside the 1. So 7 to the first equals 7, which that's also a true state. Okay, base stays base. So right here we have the 5. That's going to be our base. Other two switcheroo. 5 was by the 125, so now it'll be by the 3. And it will equal 125. That is also true. This last one, base stays base. So 64 is our base. Other two switcheroo. Now it's going to be raised to the 1/2. And that will equal 8. In case you aren't familiar with this, if we have an exponent that is 1/2, that's just the same thing as a square root. All right, so now that was going one way. We also need to be able to go from exponents to logs. Today we won't quite get into this, but eventually as we start to solve these problems, we'll need to be able to move back and forth between the two quite easily. Okay? So from exponential to log, that means we're going to have log at the beginning. So once again, same memory trick, base stays base. So in our case here, 3 is the base, so that'll still be the base. So it'll be log base 3. The other two switcheroo, meaning it was by the 4, so now it's by the 81. And that will equal 4. Base stays base, so 7 is the base. The other two switcheroo, so it'll be by the 2401, and that will equal 4. Okay. So base stays base, so this is base 12. Other two switcheroos, so the 12 will go here, equals 1. And then our final one, base stays base, so the base is 2. Other two switcheroo, it'll be to the 1/8 equals -3. All right, so now, today we're going to look at how we can solve it. Sometimes we won't have an answer, okay? We just have this. And there's a couple ways, and as the week goes on, we'll learn more ways. But today, the simple way we can solve it using our knowledge of exponents. First, we need to set it equal to the square. Now, what I mean by that is equal to the square. I don't know what that answer is. That square we have to fill in. Okay, then we're going to rewrite it. So base stays base. It'll be 3 raised to the square equals 81. And hopefully you can figure that out. 3 to the first is 3, 3 to the second, 9, 3 to the third, 27, 3 to the fourth is 81. So this next one, once again, set it equal to the square. 8 to the square equals 8 because base stayed base. The other two switch true. 8 raised to what equals 8? That will be 1. Anything raised to 1 will equal itself. Example 11 here. Set it equal. So 9 to the square equals 3. Now this one, if it gets smaller, we know it's going to be a fraction. And let's think the square root of 9 is 3, so we know it'll be 1/2. And our final one, base stays base, so it'll be 3 to the square equals 1/9. Okay, and in this case, we get a fraction. So think about it. If it's on the bottom, that means that it is some sort of negative problem. Okay, so 3 to what power gives us 9? That would be 2, so we add that negative in because it was the fraction. All right, so go ahead and flip it over to the back now, and we're going to talk about how we solve log equations. So in this case, this is the really useful part about a log, is we can solve this equation, log 3 base 3 of x equals 2. Now, in order to solve this, first step I recommend you do is rewrite it. So let's rewrite this in exponential form, and then after we do that, we can just solve. So log base 3 of x equals 2. Base stays base, so the 3 will still be the base. Other two switcheroos, so 3 to the second equals x. From here to 3 to the second is 9. 9 equals x, and we are done. All right, our next one, base stays base, so it's going to be 2 to the 5th. Other two switcheroo. That entire x plus 1 will go to the other side, because it was inside of parentheses here. Okay, because of that, that whole quantity switches. 2 to the 5th, hopefully you know 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Okay, but if not, use your calculator. That's fine. 8 equals x plus 1. Then all we got to do is subtract 1, and we get 31 equals x. All right. Our next one, base stays base, so 4 will stay the base. The other two switcheroo. 4 to the second equals 3x minus 5. So we get 16 equals 3x minus 5. From here, add 5. 21 equals 3x. And our final answer then, x will equal 7. All right. Now, the next thing we're going to talk about is the number e. Now, this number, it's defined here by this expression 1 plus 1 over n raised to the nth as n approaches infinity. As n gets bigger and bigger, this answer will get us closer and closer to our value of e. Now, I know it has an e. It's because this number shows up a lot, so it got kind of a label. Don't think of it as anything except a number, though. It's still a value. It's kind of like pi. We gave pi a symbol because it comes up so often. Okay, so keep in mind, e is just a number. All right, now this number e, it's approximately 2.718. We could keep going. It's an irrational number. It keeps going and going and going, but 2.718, okay, that's how far it is to 3 decimal places. Now, to solve these, we can use our calculator. So hopefully you guys have this calculator pinned. If not, talk to me and I can help you get it. Send me an email or something. I can show you how to get that, give you instructions. But to get e, hit second, and then over here, this ln button, as you see in the top, it's e to the x. So e, now all I have to do is, in this case, it was e to the third, hit enter, and we get 20.085. Okay, and let's see, we wanted to go to the third decimal place, so 20.08, we round up to 6. All right, now the next one, we're going to have a 5 at the front, then e raised to the 5th, hit enter. Once again, 3 decimal places, so 7042.06. We'll round that up to 6. And the final one over here, negative 2, and then e to the 6. So second e to the 6. And we get a negative, which makes sense because we multiplied it by a negative at the front, but negative 806 and 0.858. Okay, so if you're having trouble with the rounding, you're not sure I got those, please send me a message, reach out. That's something I didn't spend a lot of time on because we should already know how to round, but if not, please let me know. Okay, so now, the final thing today, we're almost done with our lesson. There are 2 special cases in logs, and log base 10, this is our common logarithm. It's the most common. It happens a lot in both nature, the world, whatever. So because of that, log 10 is just going to be written as log. It's kind of like when we take our square root, we don't have to put the 2 on there because square root happens a lot. Okay, what I mean by that is the square root, there's nothing right here, where the cube root has to have a 3. Okay, it's the same kind of idea in that log is our kind of generic version. We use it a lot, so it's just log. So on example 19 here, even though there's not something right there, there's really a 10. So if we rewrite this in exponential form, base stays base, it'd still be 10. Other 2 switcheroo. So 10 to the second equals 100. Okay, now the next thing, the other special case, log base e is called the natural logarithm. And because of this, log e, we write as ln. Okay, it's our natural log. So e to the first. If I was going to rewrite this in logarithmic form, it'd be base stays base, so log e, the other two switcheroos, so 2.718, and all that would equal 1. However, that is actually the same as just ln of 2.718, which would equal 1. So right there's our final answer. Okay, now, just like we did in our lesson in 5.4, sometimes we have the two set equal to each other, and they're both e. E is just a number, so it's the exact same concept we did in 5.4. The e's will cancel. So this goes, that goes. We're left with 2x equals 4x plus 8. So we'll subtract that. Negative 2x equals 8. Divide, and we get x equals negative 4 as our final answer. Okay, and our final one here, right here, it's just log. So we could have a 10 there. Now base stays base, so 10, the other two switcheroo, 10 to the first equals 2x minus 7. So 10 will equal 2x minus 7. We'll add the 7 over, we'll get 17 equals 2x. We divide by 2, and we get x equals 17 over 2 as our final answer. Okay. Now, to close it up, I know this was a little longer of a video. In summary, the reason we care about logs and exponentials together, logs and exponentials are actually inverses. Now I'll show you in just a second a graph. So logs and exponentials are inverses. So in Desmos here, first we know, right now I have this line y equals x, because we know if they're inverses, they'll be symmetric over that, they'll be a reflection over that, okay? Now our original one, this log, or let's start with the inverse, y equals 2 to the x. So, start with the exponential. Y equals 2 to the x. Right here in red, we know how to graph that from last week, okay? Now the inverse of that, log base 2 of x, as you can see, they are reflective, they're symmetric over that green line because they are inverses. So that's all I have for you today. We're going to keep talking about this. I don't expect you guys to be geniuses at this yet. This chapter takes some time, but keep working hard for me, and hopefully you guys have a great day. Bye.